It's a bit past 4:30 in the afternoon. Normally there should be plenty of light, so it's got quite dark. So I'm guessing, just looking out through the window now, maybe storm clouds and a thick rain cloud is blocking out the sun's rays, I guess. Anyway, so switch on the light. Right, well, continuing straight on. Now, from the very end of the previous session, we had an equation, you might even be able to see it, I'm not sure, but involving u1 and u0, the wave functions. So you can try this for homework if you like. So this actual expression here is u1 in terms of u0. So if you plug this in into the u1 of the previous expression, you may getting the two sides to be equal. So you can try that for homework if you like. Now we are in the second last chapter of the book. Things are definitely getting a bit harder, and remember this is an overview text, an introduction to quantum mechanics, what quantum mechanics is about. I use the expression flying over the icebergs, so just to tell you what quantum mechanics is about. So it's not surprising the proportion of ICBST, it can be shown that type phenomena is increasing somewhat. So here it is again. Here's an expression for E2, so the second order correction of the eigenvalues for energy, eigenenergies here. So where we're used to, for E1, you had a 0 here. Now, so in the text, it just says it can be shown, and I haven't tried to derive it. So you just accept it. You can try to derive it if you like. It's E2, so you may be able to expand out to second power in lambda squared, and see if you can find this. You can try that if you like. Right? So it's just thrown at you in the text that E2 is of this form. So with a 1 here. And given that, because you now know what E1 is, right, from here, so you just plug this into here. This is little e, big E, Z, right? That's your perturbing Hamiltonian, you know that. So plug it in and you get this expression. So you've now got, because that's what you asked in the previous previous session, to calculate the energy shift, in other words correction in the energy, to second order, right? So second order, and here it is. Okay. Right. So next example, third one, is electrons in a metal. So keep it simple. So we'll just deal with one-dimensional case. So you've got a lattice then. Periodic lattice with, let's see, what would be silicon, I guess. So you have atoms periodically spaced, distance, let's say A, from each other along a line, one-dimensional x-axis, let's say, right? So you have a periodic potential, say, of this form. So, so since the spacing is A and this potential will be periodic, so it will repeat every A. So as x goes A, 2A, 3A, and so on, this cosine goes through a whole cycle. So if you start at x is 0, you just get B0, okay? And then if x is A, well, you get cos of 2 pi. That's a complete cycle, so it's cos of 0 is 1. So if x is A, you get cos of 2 pi, which is the same as cos of 0, full cycle, which is 1, so V0. Alright? So this is the question statement. So you're asked to show there is no, here's the mathematical symbol, there is no, crossed out, there's no first order energy shift. So your E1 would be 0, unless the momentum of the electron takes this value, plus or minus h bar pi over a. Right? So normally first order shift in energy would be 0, except when the momentum has this value here. All right. So how to do that? Okay. Now, if there's no potential, no perturbing potential, there's no h dashed, okay, then the electrons are free, right? Now, we studied that case in chapter 4, way back. So the wave functions in that case are of this form. And the L here, the normalizing term, found that a bit hairy. Remember we sort of took our infinitely long one-dimensional axes and we made it a finite length and looped it in a sense so that the total circumference was L, and hence this root L to normalize it. So this wave function gets normalized. Right? That's where the L came from. Alright, the energy, effectively just kinetic energy of the particle, because the de Broglie momentum, P, is h bar k. So effectively here you've got P squared over 2, and that's the kinetic energy, like a half mv squared, effectively. Right? Now, so the first correction to the energy, E1, will be of this form, right? The diagonal. So just plug in, so the eigenfunction would be this, conjugate it, so it'll become minus I. So let's see, your potential is this, right? That's your perturbing potential, plug that in, so you get this. Now with a conjugate minus I and the non-conjugate form, they just cancel, right? Become 1. So and you're integrating over your total space, which is L, 0 to L, and you get this expression, which is 0, just from high school calculus, right? It's 0. Okay, so we've shown that there's no first order shift in general. Now we have to talk about this exception, unless the momentum of the electron is this. So where does that come from? All right. I'll turn around. Okay, now if the electron's heading the opposite, so if it's heading in one direction with here's a K particular de Broglie 2 pi over lambda de Broglie wavelength, the wave number so called. Now you could have the electron sort of going that way, but you could also have it going this way with the same energy, the same absolute value of K. Right? So these two states, the electron's going that way, the electron's going this way, they have the same energies. Right? So in terms of energy eigenvalue, that means these two eigenstates, energy eigenstates, have the same eigenvalue, this much. Therefore, by definition, these two states are degenerate. Okay? Keep saying it, but useful reinforcement. What is degeneracy? It's when you have two or more eigenstates that have the same eigenvalue. Okay? Which is the case here. These two eigenstates have the same eigenvalue. This. So we have a twofold degeneracy. The number here just talks about how many eigenstates with the same eigenvalue. Well, 1, 2. Right? Okay. Now. Thank you. Explained. Now I put rather cynically here 2 exclamation marks, question mark, and exclamation mark. I didn't find Davies, the first author's explanation at all clear. You need to know some linear algebra, and while I'm talking about that, let me give a plug. I've done this before. This is the textbook that I'll be using. It's at undergrad level. You can see here undergrad text in mathematics. It's by Serge Lang, who's a rather famous name, especially with Springer, the publisher. He's written lots of, mostly graduate level texts for Springer, so I guess he's one of their favourite authors. So this is a text I'll be using for an undergrad course on linear algebra, and the techniques to... can you remember from earlier theory, a few sessions back, there was an expression for the error correction of the energy involving differences in the energy eigenvalues that were in the denominator. Okay. And so if you had eigenvalues that were the same, you're talking about different eigenfunctions, but if their eigenvalues were the same, if you had an E... Whoa, did you hear that?